In the last lecture we discussed about something called acceptable level of risk. We said in marine structures or in offshore structural engineering, essentially the risk cannot be 0, there is some accepted level which is formulated by international regulatory agencies like EPA, nuclear reaction power commissions, etc. There are international authorities which frame what would be the minimum acceptable level of risk based on which you can operate your platforms or marine structural systems. We have also said that if the resistance and the load effect are normally distributed, the variables, or if they are log normal, then there are simple closed form expressions available to compute what we call the reliability index, and we already said the probability of failure can be simply the function of reliability index, and there is a table which we gave you in the last lecture based on which I can easily use this table to compute the probability of failure, and the reliability can be simply set as 1 minus probability of failure, and there ends the solution for this problem if the resistance and the load effects are distributed as per our notion, or the joint probability density functions can be evaluated in a closed form as you see here. So, the emphasizing point here is the probability of failure will be on the same time frame as that of your R and S. R and S. Suppose for example, if probability of failure is annual, then R should be the annual maximum value and S should be correspondingly the load effect of annual peak load, and so on. So, depending upon the period which is associated to the probability of failure which you are looking at, accordingly the variables which will govern the probability of failure will be capturing the same time. On the other hand, beta, the reliability index, has the same time frame as that of the variables R and S. That is what we concluded in the last lecture and said that reliability index cannot be applied for an infinite time. There is a time frame within which you can apply the reliability index, because this time frame is essentially depending upon the time frame of your variables R and S, and we also said margin of safety M can be simply R minus S. If this is exactly 0, let us say it is just on the virtue of failure. Okay. If R is greater than S, it is safe. If R is less than S, it is unsafe or failure mode. Okay. R is resistance and S is the load effects, that is why S is standing there as load effects. Now we will see what would be the implicit failure probability which is applicable in the design. So, we like to see there are two variables here, one is the resistance or the strength of the material, other is of course the load effects coming on the material or on the member or on the structure. Out of these two, the probability of failure or reliability is governed by which of these variable more seriously. We would like to look at that. So, what would be the effect of this implicitly, not explicitly, inbuilt, okay, inbuilt failure phenomena which can significantly influence my design in probabilistic terms. That is what I am looking at in this topic. Okay. Let us see that how we will, by through an example we can easily illustrate which of these two are more important. Does not mean that the other is less important, both of them are variables, both of them have uncertainties which are irreversible, reversible. We have seen all of them in the last few lectures. Okay. All of them are equally important, but amongst these two, if one has to look at the superiority level, let us see how it is affecting the design. For the random load effect, S and resistance R, they be represented as below, because we need the statistical characteristics of these variables. What are the statistical characteristics of these variables? Mean and standard deviation and variance. Okay? Let us see that. Let us say mu s, that is for the load effect, which can be taken as Bs into, let us say, Sc, where in this case Bs is less than or equal to 1.0 and the variance is lying between the value of 0.15 to 0.30. Similarly, mu r Br into Rc. Okay, in both these cases the subscript C stands for characteristic value. We understand what is the characteristic value of the strength and what is the characteristic value of the resistance. Okay, we know this already, we have defined n number of times, we must be knowing this now. And Br is greater than 1 and Vr is, let us say, 0.15, that is the variance of the resistance. If the resistance R and the load effect S can be represented by these two parameters in this order, you may wonder that why Br is more than 1 and B is less than 1. Can you give me why it is so? Yeah, we have to look for the more, that is the general aspiration to be. Okay? So, that is what we are saying, this is less than 1 and more than 1. Similarly, this can be 0.95, this is 1 by 0.95. Okay? So, it is more than 1. Okay? That is what we are saying here, for example, right. So, if these two are there, let us substitute this in my beta index problem and see what happens to my reliability index. Now, specifically beta S reflects the ratio of the mean load. Why mean load? Because I am looking at the mean of S. Suppose we are looking for an annual variation. If the period of variation is annual, then beta S should refer to the annual maximum value. Okay. And therefore, one can say Pf is also annual. Now, the characteristic values as you see here, maybe Sc refers to the characteristic value of the load effect, which is typically a 100-year return period, is it not? That is what we are looking at. Okay. Let us assume that let R and S be log normal, then beta ln, which we saw the expression yesterday, can be approximately equal to square root of VR square plus Vs. Now, let gamma R and gamma S, what are these? These are partial safety factors, okay, for resistance and for the load effects, be 1.5. That is a typical value what we have in most of the international codes. Let us take Bs, it should be less than 1, I take this as 0.8, okay. Let us take Br as 1.1 and we already know Vr is 0.15. We also have another expression which is derived from this by substituting for mu r mu s and Vr Vs, which can be ln of Br by Bs gamma s gamma r by square root of Vr square plus Vs square. This is also an approximate value. Let us substitute this. So, Br already I have as 1.1 by 0.8 multiplied by 1.5 divided by square root of please make a correction here. Vr in this case is 0.1, not 0.15. Please make a correction here. So, Vr is 0.10. So, 0.10 square plus Vs square. Now, I have a band of Vs varying from 0.15 to 0.3. Okay. Let us say for Vs equals 0.25, my beta ln, can you find out this value? This comes to 2.7 and for Vs 0.2, that is in the same band, beta ln comes to 3.2. So, for a very small variation in the variance of the load effects from 0.25 to 0.2, where when Vs is decreasing, beta ln is increasing. So, we can simply write so I can also use the table and tell me what are the corresponding probability of failure. For beta ln of 2.7, what is the probability of failure? For beta ln of 3.2, what is the probability of failure? Okay, 3.5 into 10 power minus 4, and for 3.2 minus 3, and for 3.2 let us say 7, okay, 10 power minus 4, okay. Now, we can see a very drastic difference in probability of failure for a very small variation of Vs. Okay. So, what we can say is beta ln is inversely proportional to Vs. Okay. So, what does it mean? The variance of the load effects significantly influence the probability of failure and it is inversely proportional to beta ln. Okay. It is very interesting. It all depends upon how accurately you model the random variables in the load effects and find the parameters of mu, variance, etc. If you make any mistake or any data omission in calculating the first order second moment values, let us say mean, standard deviation, variance of the load effects, forget about the resistance, here we are fixing it. Okay. It can significantly give a very different sense of the meaning for your reliability or probability of failure. This is an implicit effect of the probability of failure in the design. Okay. It is nothing but a statistical variable of the load effect which can affect my design sense very seriously, because it is very much different. Okay. Or even reliability index is very much different, right. It is a very important, let us say, the illustration through an example that how these parameters can sensitize the probability of failure in the design. Okay. Now, let us talk about how reliability framework can be useful in ultimate limit states. One can say the ultimate limit state and reliability, let us say ultimate limit state can affect or influence the design since the method is based on maximum loads, maximum load effects, or I can even call this as the extreme load effects. So, that is one statement, how ULS can be influenced by the load effects, because it is based on extreme load effects, that is why we call as collapse load. Okay. Whereas, ULS is also affected or influenced by the traditionally determined strength of material parameters like yield strength, Young's modulus, which are related to strength of the material or resistance factors. Now, these are generally supported by good and extensive test results. Okay. Generally, you do not find the resistance parameters ad hoc, you conduct tests by on different samples, take a proper mean. So, all these will have a specific implication on your ULS. That is why in this equation, if you see, generally the variance of the resistance is closely fixed, is not given a band. whereas the variance of the load effect is given a band, because there are high degree of uncertainty in the load effects compared to that of the material strength, because material strength is calculated more or less in a very systematic manner with the experiments in the laboratories. Okay? And there is an extensive quality control in manufacturing of this material, therefore, there is no much variation, though there is a variance here. Okay? We are not saying it is 100% right, but it is limited to a very narrow band of only 0.1. Okay, whereas here, and this has sensitized the beta ln as we saw in the last example, by small variation of 0.25 to 0.2, beta ln probability of failure indirectly are affected significantly. Okay. So, Vs or variance of load effects sensitizes the probability of failure significantly with respect to or in comparison to that of the resistance or strength of the materials. So, one can clearly come to a conclusion saying that thank God to the manufacturing process and the quality control implemented by people, our variation uncertainties on the resistance factors of the material is far narrow compared to that of in the load effects. Now, one can ask a question, why I cannot compromise or let us say find out this to a higher accuracy. As I said, they are caused by randomness in nature, they are irreducible, I cannot control on them. That is the reason why the variance in the load effects are higher. It is not because that we do not know, we do not have a mathematical process of narrowing down this variance, it is not that. It is caused by the randomness in nature, which is unexpectedly or cannot be modeled correctly. It is because of the reason we say that this is having a larger band compared to that of the strength of material. Now, ULS, which is a design process which is affected by two factors. One is load effect. Now, in this case we say ultimate limit state, we are talking about extreme loads. UL is also bothered about the traditionally determined parameters. Now, let us look into these two and reliability framework and see how this can affect the reliability framework on ULS. Therefore, based on these two, the reliability framework is based on establishing a limit state function, that is what we have seen yesterday, which is G, is it not? That is what we have seen yesterday. This limit state function can be time invariant, can be time variant. That is what we saw in the last lecture, how y of t can cross the outcrossing of the limit boundary to find out the probability of failure. We have seen two different curves in the last lecture, we have found out how the limit state function can be established. So, essentially reliability is establishing the probability of exceedance of limit state boundaries. Is that clear? You form a boundary and you are looking at what is that probability that this boundary will be outcrossed. So, that outcross means failure, not crossing means safe. Is it clear? So, I am looking at the outcrossing of the boundary, which is established by a limit state condition, and reliability is not 100% accurate. Only because of this reason, establishing the limit state function itself is a difficult task, 1. 2, determining the joint probability density function or integrating this over a domain of the limit boundary itself is complex, okay, which we have seen in the last lecture. Having said this, let us now take single value of R and S and see how this affects my ULS. Then we will take multiple value of R and S. Let us say for a single R and S, that is resistance and load effects, the limit state function is given by G of R and S can be simply R minus S, call this equation number 1, Okay. Now, we already know that since R and S are subjected to large uncertainties, the preferable design format is simply using a safety factor on this. Okay, that is what we have done in the design. So, we should say the characteristic strength of the material by gamma r, is it not? That is the safety factor of the material, should be higher than or greater than the safety factors what to use for load 1C plus safety factor what to use for load 2C. This C stands for the characteristic value, and there can be 2 loads or 3 loads like this. Okay. And gamma S1, gamma S2 are respective factors for different kinds of loads, because as we all understand, given in API, given in ABS, the load safety factors are not same for all kind of loads. Okay. Somewhere it is 0.95, somewhere it is 0.9 and so on, right. So, I call C equation number 2. So, in this equation number 2, I should say where the subscript C stands for characteristic values, R stands for resistance, and S stands for the load effects, nu R is I should say resistance factor, and nu are S1 and nu S2, or I should say load factors. Having said this, we also know that resistance refers to a characteristic strength of 5% fractile material strength. The variation in the material strength is only 5% or within 5%, 95% does not vary, okay. Whereas the load effects refer to annual probability of exceedance of 10 power minus 2. I think this we had discussed in the first module, if you remember. It is understood that the characteristic value of load means that the probability of exceedance is 1 in 100, okay. That is what it means for the characteristic strength of load. Now, the design criteria is now given by let us say limit function of RD S1D S2D should be greater than 0, should not fail, that is a successful design, okay. Equation 3. where D subscript all stands for design. We can also say where RD is RC by nu R, that is my design value, is it not? That is how I take it in the design. And S1D can be S1C nu 1C, S2D can be S2C nu 2C, which are all called as design values. Now, the expression for failure is given by G of R equal to 0. Even if it is equal to 0, okay, it is said to be failed because it is on the verge of failing, right. R minus S is the margin of safety. If it is set to 0, it is failed, it is on the boundary. Okay, if R greater than S is safe, R less than S is unsafe. That is why we say it is less than or equal to 0 is my limit function. Okay. This is for a single value of R and S, where we can easily find out this. Now, if you have got multiple R and S, then how do you go about it? What do you mean by multiple R and S? The structure can be subjected to different load combinations. For example, there can be an effect of axial load, maybe tension or compression and bending. So, it is a multiple loading effect. Okay. Multiple R and S means it is not that there are different varieties of loads, that is already there in the previous case also, S1, S2, S3 etc. But we are looking now at the combined effect of these forces or effects on the member, that is what we call as multiple. Yes. What do you understand by multiple R? I have got a composite section. The strength of the material can vary between the two sections are composed together to form a single unique material, where we address already said functionally graded materials. Okay. Can have a multiple R problem also, depending upon what I am going to recommend for my design. So, that is the meaning of multiple R and S. In that case, failure criteria can be formulated as G of R1, R2, R3, S1J, S2J. I will come about that what is J. Can be given by 1 minus S1J by R1 which can be also said as 1 minus x1 by x2 plus x3 be 1 minus x1 by x4 of x5. Why this is x1? Because it is same as this, okay, same as this. Equation number 5. Where S1j, S2j etc. are load effects for different combinations, and R is the resistance. Essentially, the count J stands for different load type. Now, equation 5 is based on Perry-Robertson approach. That is a very famous approach in reliability analysis. Whereas, in which R1, R2 be the axial force and R3 be the bending moment, sorry, the Euler's law. Axial force, okay, and bending moment capacity together, and R3 be the Euler's law. Now, in the practical design, R and S are used by means of their respective characteristic values. Whereas, in reliability, they are considered as random variables. That is how they are differentiated in the ULS and the reliability framework. Now, the partial safety factors that is gamma Si 1, 2 etc. for different loads are computed using the structural reliability theory so that the design equation, what was the design equation we gave in the last one, single R and S? I think we said the design equation will be R by safety factor and S by the safety factors, S into multiply with equation number 3, 3. That is the design equation given in equation 3 corresponds to the target failure probability. So, this is a variation what we use in case of multiple R and S compared to that of single R and S. So, there is a one-to-one correspondence between ULS, that is ultimate limit state design methodology, and that of reliability. First correspondence between these two or similarity is in design applications we consider them using characteristic values, whereas if we really want to consider them in reliability problem to find the probability of failure, we consider them as random variables. Okay. So, to amalgamate or to mix up or to have influence on one over the other, what people have done is estimate the safety factors using reliability theory, that is where reliability is bridged to ULS. So, if you are able to estimate the partial safety factors using reliability theory and targeting the probability of failure, that is equal to 0 or greater than 0, less than 0 means for sure it is going to fail, estimate the safety factors based on that concept and use that safety factor in a design, that is how reliability theory and ULS are bridged. Is it clear? That is how they are connected together, right. So, one should have a rational way of estimating these safety factors using reliability theory, where the parameters contributing to this, that is R and S, are considered as random variables. Okay. Once it is obtained, use it in the design as characteristic values and do the design. So, it means that the design used by calculating or employing these values will have a defined probability of failure which you already know, 10 power minus 3, 10 power minus 4, you know. 1 in 10,000 structure, 1 in 10,000 may fail, that is the probability of failure if you use this gamma SI in your design. You understand, this is how they are arrived. Is it clear? That is how ULS and reliability theory are bridged. We stop it here, we have the next lecture discuss it in detail about this and move on to the levels of reliability theory. Okay? Thank you.